this is another example of drug resistance for EGFR inhibitors. So EGFR oncogenic mutations is a key driver mutation for non-small cell lung cancer. And the EGFR inhibitor can inhibit this EGFR triggered pathways to block the downstream cell growth. But again, you guys can see that there are so many pathways that can trigger downstream signalings. And blocking this one pathway does not work at all. And even that it could work at the very beginning, the EGFR gene itself can also acquire a different mutations called the T17-9M mutations to make sure even the drug cannot target this gene after this mutation. So this table is from a review paper summarizing so many different mechanisms of drug resistance from different studies for different drugs. And we can summarize all of this mechanism into three broad categories of drug resistance. The first category is called alteration of drug target. So for example, the genes, the oncogene can simply get a different mutations, and then the drug cannot block the pocket after that. And the second is called pathway activations. This is a perfect example. You block these genes, then the cancer cells can figure out some way to activate the downstream genes. So then you can keep signaling and keep growing after that. And the third pathway is more universal for many drugs. It's just simply the bypass mechanism because there are so many pathways on parallel. You can just somehow change a different path to trigger the downstream signaling. And in recent years, there are more and more studies on the mechanism of the drug resistance for immune targeted therapies. I think that Avi might talk about this more in the next time. This is a brief summary table of current known mechanism of immune therapy resistance. But the basic take-home message is that cancer cells are so smart. No matter what is the method you use to treat them, they can always figure out some way to counter your therapy, to figure out a different way to keep growing. So could someone have a think or make a guess or like give reason here why tumor cells, they are so smart, why they can always find a way to get the ability of drug resistance? Okay, maybe from maybe the lady first and the second. Yeah, perfect. Actually, you give the right reason. But do you have something to add?
Just in addition to that, like natural selection.
Exactly. Perfect. Natural selection. So like the tumor cells just keep proliferating, just keep their proliferation. And until the time point that you find this tumor, you want to treat that, there are already a significant amount of heterogeneity. There are always some major populations that can survive the drug attack. And what makes the situation even worse is that the cancer cell is an unstable system. Their DNA repair pathways, their proofread mechanism all go into the wrong situation. So they can acquire lots of mutations at a much higher rate than the normal cells, such as they can gain somatic mutation quite rapidly. And also there are lots of copy number variations in the genome. They can open and close some genes in quite a rapid speed. And there are also lots of epigenetic variations in the cancer cells to trigger the overexpression or to mutate, to silence some genes. And because the cancer cells is an unstable system, they acquire a much stronger power of making the evolution. So they can always find some way to evade the therapy attack. So, but anyhow, when you face some challenge, you are always going to figure out some mechanism to understand what is the common mechanism that the cancer cells utilize to evade the therapy treatment. So in the next several slides, I'm going to introduce some basic research method that people use to figure out the cancer therapy resistance mechanism. Ideally, you can collect lots of clinical samples of patients. For example, the patient with good response and the patient with bad response, and do the genome-wide sequencing, do the gene expression profiling, and compare their genomic profiles between the responders and the non-responders to figure out what is the potential oncogenic mutations that trigger the drug resistance. But this is only the ideal scenario. In reality, it's very hard to get that amount of data. This is an example of some studies to find the mechanism of intrinsic resistance of immune targeted therapies. You can see that for most of these studies, they only sequenced about 40 patients. But remember, there are 20,000 human genes as potential variables in your study. And in statistics, we define a problem as a high dimension if the number of features, which the genes, is much larger than the number of patients. It is inherently very hard to get a robust feature selection result and analysis in such ultra high dimensional settings. So the first big hurdle is the ultra high dimension of most cancer clinical data set. And meanwhile, for many situations, it's very hard to profile clinical samples because when the patient develops some drug resistance, they will not let you to get more biopsies from their body because this is not going to help them. And more biopsies might actually give them a higher risk. And then it's still very expensive nowadays to sequence lots of tumor samples. Meanwhile, even after you get lots of samples and find some potential mutations, it's impossible to do genetic manipulations on the clinical samples. Because they are human samples, you cannot do the experiment on humans. So nowadays, most people use the preclinical models to simulate tumors and to study the potential drug resistance mechanism. Preclinical models include the immortalized cell line and the mouse models. A particular advantage of the preclinical models, especially the immortalized cell lines, is that you can use the automated compound screen platform to measure the drug response and test their association with the genetic variations on a massive scale. A typical framework of compound screen comprises a compound library with small molecules with different structures, as well as a cell panel with different genetic background. Then the modern robotic technology can test almost all pairwise combinations between your compound library and different cancer cell line panels and get the drug sensitivity. And the molecular profiles of these cancer cell lines are also typically already profiled before the study. Therefore, you can apply lots of statistical analysis to know what is the downstream variation that are associated with the drug sensitivity. Here are some examples of large-scale data set of compound screens from the Sanger Institute and from Novartis. You can see that they screened thousands of compounds on, or even tens of thousands of compounds on the cancer cell panels. And after you got compound screen data, you can get the drug sensitivity measurement as the IC50 value or as the area under dose response curve. And then you can do lots of statistical analysis to find what is the most important genetic variations that are associated with the compound sensitivity. And then you can see that sometimes when the cell lines have certain type of mutations, the cell line will not respond to the anti-cancer compound treatment. Then maybe this kind of mutations could be the key drivers of promoting the drug resistance. But there are several pitfalls you need to be aware for the compound screens. First of all, in the compound screen study, whatever you get is always an association effect. Something is correlated or associated with another effect. And association is not causality. You could get association due to many kind of artifacts. And it's always important to somehow genetically knock out these genes and evaluate by genetic approach. And second, compound screens are largely limited by the composition of the cell lineage. It's very hard to establish very good cancer cell line models for a specific disease. So for example, like the NCI 60 cell panels only have probably 1 or 2 cell lines for each cancer types, which means if you want to study one specific type of disease, you may not have sufficient cell line lineage representation for that specific disease. And the second common approach that people use a lot to study the anti-cancer drug resistance is the genome-wide loss of function screen, which is one of the key focus of research at the Shirley Liu lab. The basic idea is that if you can get rid of a gene in the cell and see what's the genetic effect of the gene knockout or gene activation, then on the drug sensitivity, then you will directly know whether or not this gene is related with a gain of a drug resistance. But the thing is, we can knock out the gene individually one by one. Can we do this on a massive parallel manner? Or can we do this for many genes in the high throughput way? This is the idea of doing the genome-wide compound screen through the CRISPR-Cas9 technology. So the CRISPR-Cas9 technology can knock out each gene specifically by designing a guide RNA targeting the gene region. And in the genome-wide CRISPR screen experiment, you first synthesize lots of DNA oligos, and each oligo is targeting one specific gene in the cell. And you make the viral package and make sure that each lentivirus is delivering one specific oligos or one specific guide RNAs to inhibit one specific genes. If you infect a pool of cell lines with really low concentration of the virus, you can assume that each cell only take in one virus, and the virus only knock out one gene in that cell. So you get a population of cells in each cell, there's only one single gene knockout. Then you can split this population, treat them with an anti-cancer drug, or treat them under some control conditions, and compare the frequency of the guide RNAs in two different conditions. The readout of a CRISPR screen is very simple. It's just a fold change ratio. The abundance of the guide RNAs in the treatment conditions and the abundance of guide RNAs in the control conditions. If this log fold change ratio, if this fold change ratio is bigger than 1, this means that the gene knockout will make the cell grow much better under the drug pressure. So the activity of these genes is actually enhancing the drug efficacy, because knocking it out will make the cell line grow much better. If this ratio is smaller than 1, this means that knocking out this gene will make the cell line grow not that well. This indicates that the activity of that gene is repressing the drug efficacy. But like right now, there are lots of genome-wide CRISPR screen data sets available from public domains, and also Shirley Liu Lab is also doing lots of genome-wide CRISPR screens to understand the mechanism of drug resistance for lots of targeted cancer therapies. So it's a very powerful technology because you can do this type of test almost on whole genome scale. This technology is very powerful, but still, every technology has some limitations. When you are using this technology, you need to be aware what is the potential limitation of this technology. So I have listed a few limitations of genome-wide CRISPR screen here. So first of all, the genome-wide CRISPR screen assumes that each gene knockout cells must have sufficient frequency at the very beginning of the experiment. Therefore, you can analyze the relative fold change ratio after a period of drug selection. But is this assumption always realistic? Probably no, because first of all, the DNA synthesization technology right now cannot make sure all of the guide RNAs will be synthesized at an equal frequency. Typically, some guide RNA sequence patterns will be easily synthesized for many times, but some sequence patterns are kind of harder to be synthesized. And all of the essential genes will be quickly depleted after the viral delivery. Therefore, at the very beginning of the experiment, you might actually get a down representation of some essential genes. And second, the CRISPR screen experiment assumes that one single gene knockout can tell you the genetic effect. But remember, our human beings have lots of redundancies. We have typically many paralogs of the same genes with redundant functions. Therefore, knocking out one gene may not really reveal its true genetic effect by compensation from other genes. And third, the genome-wide pool screen assumes no cell-to-cell communications, but cell signaling is very pervasive in tumor ecosystem. So the genetic knockout effect in one cell might be covered but the signaling from the neighbor cells.